I'm going to be talking, hi, my name's Forbes. I'm going to be talking about creating a domain-specific language. I'll first cover what is a domain-specific language, or what do I mean by a domain-specific language, then why you might want to create one, and finally how you would go about creating one. So first up, what is a domain-specific language? Well, all programming languages exist on some spectrum, from general purpose to domain-specific. At the general purpose end, we've got languages you'll be familiar with, like JavaScript and TypeScript, Rust, and so on, C#, Java, etc. As we add, say, JSX into JavaScript, it becomes a bit more special purpose. We start thinking about it as being really a language for creating web front ends and native applications. A bit further towards the other end of the spectrum, we have languages like SQL for manipulating databases and querying data. Further along, we have languages like Pug, Moustache, Handlebars, and so on for generating HTML, so templating engines that simply take some data and produce some HTML for a web page. Right at the domain-specific end, you can think about languages like Markdown. You wouldn't necessarily think about it as a programming language, but it is text that is ultimately evaluated by a computer. And really, it has only one purpose, which is to generate some form of rich text document from text. And it's really this end of the spectrum, these domain-specific languages, I want to talk about today. So coming back to what is a domain-specific language, for the purposes of this talk, I mean something that is a very simple language. It has no unbounded loops, no recursive functions, and it's very highly specialized. I want to consider these languages because they're much easier to build. This is a much more practical thing for you to decide to create than for you to create an entire fully fledged general purpose language. And because these restrictions, in particular lacking unbounded loops and recursive functions, make it much easier to create something that can securely evaluate untrusted user input. So why create a domain-specific language? Well, one of the times that I created a domain-specific language, I was faced with this task: automatically determine the margin before a sale is completed. So I worked at the time at an e-commerce company where we would sell a variety of different products to our customers and then have to purchase the product from our supplier. And depending on which supplier we purchased the product from, we'd have different deals in terms of discounts and rebates with that supplier. And that's what would ultimately determine the revenue that we would make on that sale, or the margin we would make on that sale, rather. So the current approach at the time was to make these deals with suppliers to say, hey, we would make a deal with, say, Apple and say we get a 1% discount when we purchase it in a given store. These I just made up. These are not the real deals that company had with their suppliers. I don't even work there anymore. But they would have these deals, some of them quite complex, some of them very specific. We would get certain discounts or rebates only if the item was in a certain product category, purchased on a certain date, the total order value was a certain amount. And these exact percentages would determine what margin we made and how much ultimately money we were making. So we wanted to be able to automate this, and this spreadsheet wasn't going to allow us to do that because ultimately the conditions associated with those margins were written in natural language in English. So the suggested approach was to build some kind of rule builder. The task I was given, the expectation was that we would create some kind of user interface that allowed us to allow the people negotiating these deals to enter and structure all of the conditions that we would then store in a database and be able to compute which discounts we were going to get on a given product. But I've seen those kind of rule builders in the past. One of these is Microsoft Outlook's rules engine for automating the filing of emails. The other is Google Mail's system for similar purpose. These things get very complex, very fast. I felt like it would take us actually quite a while to build something like this. They're complex things to build and design. And they're really hard to use. They are painful and slow to use, and they are difficult to use. So I wanted to come up with something different. And what we decided to do was create a domain-specific language for encoding these margins, these discounts and rebates in text. And the result of that was something that looked a bit like this. Each line would always begin with a percentage, then either discount or rebate, and then optionally have any associated conditions. And those conditions would be one of many different types of conditions, joined together with ands if there were multiple conditions. We structured this as close as possible to the way that our users were already writing these things into the spreadsheet. So we saw that they were writing the percentage, then afterwards they would write the condition. And so we structured our language in the same way to be familiar to those people. The users of this were not software developers. They had no prior familiarity with any kind of programming language. And yet they picked this up very quickly just from being given a few examples. And the advantage of this versus us creating the user interface, one of the biggest advantages is you can copy and paste an example. So you can take that example that we provide and simply copy and paste it and then edit it to suit your needs. And in particular, if you have many different companies with similar deals or similar structures, you can copy and paste between them and then just edit the bits that are different. And yes, you could create an import button, export button, or a duplicate button, or whatever it may be on the rules engine approach. But that's actually much harder it's something you have to specifically teach users how to use. Teach them that they can export and import, or teach them that they can click the copy button or the duplicate button. Versus if it's just text, everyone knows, or at least computer literate people are aware that they can select some text, copy it, and paste it. That's not something we had to teach them. The next advantage is the complexity actually scales really well. So we can add an unbounded number of possible types of condition without making the simple cases any more complex. It doesn't add any visual noise to the user interface. And especially if there's a condition type that's only used very rarely or only used once or twice, only the people who actually need it need to know about it. And it doesn't add any complexity to the people who are not using it. And because it's natural language, because it's just written in something that approximates English, these are legible to everyone. Everyone can read these. And we particularly approach this to match closely to what they were already writing, like I say, but being very specific and explicit, so there was no ambiguity. We removed the ambiguities in what they were writing, and removed the inconsistencies in what they were writing, but otherwise it already matches. One downside versus a user interface, it is admittedly not as discoverable. When you've got a user interface, you can look at and see the possible options that are available, and with this, we relied heavily on those examples that we provided to create that same kind of discoverability. We could have given them a general purpose language instead. So another option would have been to say, hey, you can write JavaScript into this box, and it gets passed a load of input and it returns the percentage discount or rebate. The advantage of going with the DSL, though, rather than general purpose language, is it's generally easier to read and write. So providing that the tasks you want users to be able to encode are relatively simple, you can create something much easier for them to use by designing a language around their needs rather than using a general purpose language. It was also easier for us to sandbox, so it doesn't have these complex loops. It doesn't have nearly as many features. So we're not trying to figure out how to lock down and sandbox something that starts out very broad. Instead, we're just adding that very minimal set of functionality that we need. The downside is the functionality is limited. So everything that we needed them to be able to do, to some extent, we had to create a way of doing that in the language. It could also be hard to integrate with other services. If we wanted to be able to call external APIs and that sort of thing, like adding that functionality to a domain-specific language you've built is difficult. And there's also no existing tooling. So if you create a domain-specific language, it's up to you to create the syntax highlighter, the parser, the autocomplete, code completion. Like none of that stuff comes for free. And we built a syntax highlighter and we built code completion to make this easier to use. And in our case, we wanted it to be integrated into our web application, so it didn't really make a huge difference. But if you're creating one of these domain-specific languages, that is a key thing to consider, is that the tooling doesn't exist for the language you're about to create. So like I say, we've talked about why you would create a language. Why wouldn't you create a domain-specific language? Well, if you are creating a system for plugins and you expect a broad range of capabilities for your plugins, then asking people to learn a new language just to create plugins for your system is not necessarily ideal. it's often better in that circumstance to let people write JavaScript, let people write TypeScript, and then at least if they are learning something for the first time, they're learning a transferable, reusable skill, and there's also a higher chance that some of your users might already know how to use those technologies. And they're also better designed to scale to more complex systems than anything you're likely to design yourself. So if it's simple and narrowly focused, a domain-specific language makes sense. If it's broad and complex, it may be better to use a general purpose language that already exists. So let's say that you've decided you want to create your own language, you want to create a domain-specific language, you have a use case that matches this, where a user interface would end up complex and messy and frustrating, and a general purpose language doesn't make sense. Well, the first thing you're going to need to do is think about building a compiler. And a traditional compiler has multiple stages. You might have a lexer, a parser, a linker, a code generator, but I don't want you to get scared off by this. The lexer's job normally is to take your input text and break it up into tokens so that you have the individual words and symbols separated as opposed to dealing with it letter by letter. These have been traditionally part of compilers, but I think they're less necessary and you don't see them used anywhere near as much in languages that are written and built in JavaScript, because JavaScript already has things like regular expressions, so it's easier to directly parse the text. So we can skip that, and that will save us some complexity. We will need a parser, and we'll get to that in a moment. The linker's job is to link together and identify which symbols match up, which keywords and identifiers match up in your code, perhaps link together code split across multiple files. We're creating a very simple language. We've already said that we're only going to create a domain-specific language if our use case is very simple. So we're probably not going to need a linker as a separate step either. And then finally, a code generator. So we will need some way of actually running the code that we've parsed, but we don't really need a code generator. We can instead get away with an interpreter. And the advantage of using an interpreter is it's much easier to build, and it's certainly much easier to make secure. And the only downside is that the performance will be significantly worse. But because we're keeping our programs small and simple, it's unlikely with a domain-specific language that this level of performance is going to be that critical. So now that we've simplified this down, we only have two components to build. We need to build a parser and an interpreter. If you've looked at creating your own language before in JavaScript, you might have come across this concept of parsing expression grammars and perhaps the library peg.js. It can be really useful for creating and prototyping languages, but it does have a number of problems. The way that peg.js works is you use this domain-specific language for building a parser and define the types of tokens and the types of expressions within your language. So like I say, it's useful for prototyping, but it's very easy with peg.js to make, or any form of parsing expression grammar, to make parsers that are extremely slow, and in some cases infinitely slow, which can lead to security vulnerabilities. So if you're allowing untrusted user input, and then you want to parse that using your parser, you're going to have to be very careful when building a parsing expression grammar not to produce something where it can get into an infinite loop. You also get no TypeScript. You get no types for the resulting AST if you build it using a parsing expression grammar. And you have little to no control over error messages. There are ways to customize the error messages, but it's very limited and very difficult. So sometimes you'll get good errors out of a parsing expression grammar. Sometimes you'll get error messages that make absolutely no sense. The next option I see people consider a lot is, can I just create one enormous regular expression that parses my entire language? And to this I say, don't, please don't, and seriously don't do this. Couple of reasons. One is regular expressions are very, very difficult to read. It's very difficult to figure out after the fact, what does this regular expression do? It's also very easy with a regular expression, again, to accidentally make one that is extremely slow for some use cases. You'll see this all the time. If you have any JavaScript repository on GitHub, you'll get security notifications from time to time. This library has a RDOS vulnerability in it. That means they used a regular expression and they didn't get it right. So it happens a lot. Try not to fall into that trap. And then the final reason not to use regular expression is that regular expressions can only parse regular languages. That's what the regular bit of a regular expression means. And that means you cannot ever parse a language that has nested parentheses or nested expressions. using regular expressions, because that nesting means that it's not a regular language. So we've avoided those pitfalls. We're going to write our own parsers. The first thing to consider in designing our language is, how do our users talk? So in my example, I had this nice spreadsheet of what did they use, how do they normally express things. So what I did was take that language and try to distill it and make it as explicit and specific and consistent as I could, and design a language around that. I'm not going to use this example going forward in this talk. Instead, we're going to look at parsing and evaluating a mathematical expression. So we're going to deal with just integers, multiplication, addition, subtraction, division, and parentheses. And we're going to build together a parser for that language. So the first step is to define the abstract syntax tree. So this is a set of nodes that define the structure of that code. So if we were going to represent a mathematical expression not as text, but as object, what would it look like? Well, we'd have one type of object to represent integers. So that's my integer node, and it has the value of that integer. And we might have another type of object to represent a binary expression, which has an operator, which is one of the operators we support, multiplication, division, addition, and subtraction. And it would have a left side and a right side of that expression. And those themselves would be expressions. So this gives us an overall type for expression, which is either an integer node or a binary expression. And those binary expressions then are made up of nested expressions. And in both cases, I've said that these are types, these extend the AST node type and have a location. And that location just allows me to identify where in the source code did this node come from. And that will mean that if I'm evaluating this later and I support any kind of runtime exceptions, I'm able to figure out where did that exception originate in the source code and give much better error messages. So now that I've defined the AST, it's time to actually build the parser. First of all, I'm going to create a couple of utilities. I'm going to build a class. Don't need to worry too much about this, but all I'm really doing here is saying I want to encapsulate the original source string that I was given and the remaining source that I have not yet parsed. And then I've got a couple of utilities I'm exposing just to really make it easier to access. Hey, the remaining source, I want to see if it starts with something. I want to match a regular expression against it. I need a way to consume some more of that remaining source. And then the reason this class really exists at all is it allows me to then have a function that returns a location. So that generates the locations of those nodes, because it can compare the length of the remaining source and the original source and give me the location of that node. I'm also going to want a function to throw an error. Any kind of text-based language is going to have potential errors when you parse it. So we're going to write that function up front and make sure that it produces useful, easy to understand errors in this parser. So it's going to take in two things, the error message and the current remaining unparsed source. And from that, we'll be able to figure out the line number and the column number. And then I'm using Babel code frame. So most people will be familiar with Babel. It's a utility for compiling TypeScript and JavaScript using modern features to older versions of JavaScript. As part of Babel, they have this library called Babel code frame, which generates the error messages in Babel. You can, although it's obviously been built for JavaScript and TypeScript, you can use it with any language, and you simply need to give it the source string and the line number and column number, and it generates these really nice, pretty error messages that identify exactly where the problem is. So in this case, we've accidentally typed the word 1 instead of the number 1, and the error message we're getting here comes from the parser that we're going to build, and it says that we expected either open parentheses or an integer, and it shows the exact location where that error occurred. In this instance, PegJS actually does pretty well as well. The equivalent PegJS parser tells us we expected an open parenthesis or integer, but we found the character O. That's a decent error message. It gives us the line number and the column number, which matches. But PegJS often doesn't give an error message this clean. And because we're custom writing our error message, we can make sure it's always this good or even better. Next, we're going to need to start writing the actual functions for doing the parsing. So we'll start with a stub for the parse expression function. And all of our parsing functions are going to take in the input source and then return a pair, which is the remaining input source, and some expression. For now, we're going to just throw a not implemented exception here. and implement the rest of the parser and come back to this top level bit once we've got all of the components we need built out. First of all, we're going to need a little helper to consume white space. So given the input source, we'll consume any leading white space because we ignore white space in our language. Next up, we can write the function for parsing an integer. So this is going to check if the start of the string matches the irregular expression for an integer. And if we don't have a match, it'll return undefined to indicate that we didn't find an integer at the start of the string. If it does have a match, we'll return the remaining string by consuming the string that represents the integer along with any white space, and we'll return an AST node for that integer. So we'll identify this as having the type integer, a value which is the value of that integer, and we'll identify the location in the source code where that integer was defined. Anytime we've got a regular expression like this, I hate to read it by hand, so I like to put it into regexplained.co.uk, where you can paste the regular expression and you get this really nice, helpful diagram of what that regular expression does. So in this case, it expects the start of the line, and then there's one of two possible cases. It can either be a single character 0 or a number between 1 and 9 followed by any number of digits. So in this case, we're rejecting any numbers that have leading zeros because those can lead to confusion when you're reading and parsing those. They could be phone numbers. Maybe they're not intended to be integers, for example. So that's our parse integer function. We've now got to look at parsing parentheses. This looks pretty similar. So we first off see if the remaining string starts with an open parentheses. And if it doesn't, then we can return undefined because clearly the start of the string is not parentheses. We can't parse parentheses at this location. If it does start with parse parentheses, we'll consume that first character, that parentheses, along with any white space that comes after it. And then we'll continue to parse the actual expression within those parentheses. So we're calling that top-level parse expression function that we haven't yet finished implementing. And it will return both the expression that it managed to parse and any remaining text that came after the expression that it didn't manage to parse. We'll then check that the remaining text starts with a closed parentheses, and if it doesn't, we can throw a nice error message saying, hey, we expected to find a closed parentheses here and we didn't find it. Assuming it did start with closed parentheses, we then simply consume that closed parentheses and any white space and return the expression that we managed to parse. Now we've got these two functions, one for parsing parentheses and one for parsing integers, and these are our two kind of lowest level, smallest items that can appear within a mathematical expression. So we'll combine those together into a function that I've called parse factor. And when we're expecting an integer or a parenthesized expression, we know that we're expecting one of those two things. So we'll first look for a parse parentheses. If that returns undefined, we don't find that. We then look for parse integer. And if that doesn't find anything, we don't find that, we can throw an error saying we expected this open parentheses or an integer. So that gives us one function that now takes an input source and it returns the new input source having parsed one of these factors, and it returns an expression, which is either the result of parsing a parenthesized expression or a single integer. Next up, we're going to need to look at parsing multiplication and division. So I just wanted to run through an example by hand of how we might parse an expression that has multiplication. So in this case, we've got the expression 1 times 2 times 3 times 4. And as we're parsing this, first we'll come across the integer 1. We'll then come across the multiplication symbol, which means we know we're then starting this binary expression with multiplication as the operator of that binary expression. And we need the right-hand side of it, which we parse and find the number 2. Now we've got this 1 times 2, that's a completed binary expression. And we now check what comes next, and we find another multiplication. And so that means we're starting a new binary expression where the left-hand side is that original binary expression. And the right-hand side is the 3 that we find next, that next integer. And then this continues, we find another multiplication, and we find another integer. And then that's our completed structure from parsing this, is the 1 times 2 at the bottom, and then that is part of that expression multiplied by 3, and then that expression multiplied by 4. When we're evaluating this, when we're interpreting this, we'll recurse down to the lowest level, and the first thing we'll do is evaluate that 1 times 2 to get 2. We'll then climb back up the stack and evaluate the 2 times 3 to get 6, the 6 times 4 to get 24, which is the result of this expression. So we need to implement that function for parsing multiplication and division. And what we're going to do is we'll actually sort of cheat slightly. We'll assume that we've already parsed the left-hand side of the expression, and we're just checking here to see if there's a multiplication or division. So we take in as input the remaining source and the left-hand side of the expression, and we check for the operator by looking at the start of that string and seeing if we can find multiplication or division. If we don't find an operator, then this must not have been a multiplication or division, and we can simply return the source that was passed in, along with that left-hand side of the expression, which is now the entire expression because we didn't find the multiplication or division. If we did find multiplication or division, we can consume that operator along with any white space and then parse the right-hand side, which is going to be one of these parenthesized expressions or an integer. So we parse that factor on the right-hand side, and then we get from that the remaining string after this entire binary expression along with the right-hand side. So we're then going to need to check if there's another multiplication or division after that, which we do by recursing in, calling parse multiplication and division again, passing in the remaining string and that binary expression that we managed to parse, which is the left, the right, and the operator. And that will build up that string. This function, if we gave it the string from the 1 times 2 times 3 times 4, if we gave it the left-hand side as being the integer 1 and the right-hand side as being times 2 times 3 times 4, this would correctly parse and produce that structure that we had before. So next up, we're going to do parse addition and subtraction, which looks very similar. So again, we're going to take in the source and we'll assume that the left-hand side has already been parsed and resulted in some expression. We'll check for an operator, which this time is addition or subtraction. If we don't find that operator, then this isn't addition or subtraction, and we return just the left-hand side along with the source unchanged. If we did find an operator, we now need to parse the right-hand side, and the right-hand side of an addition or subtraction might actually be multiplication or division. So first of all, we'll parse the factor, like the thing that comes after a plus sign or a minus sign is always going to be an integer or a parenthesized expression. So we parse that factor, and we take the resulting source after that factor along with that factor, and we give it to parse multiplication or division, and it checks to see if the thing that came after that plus or minus sign was actually a multiplication or a division. And then we get the result of that, which is the remaining string after this entire addition or subtraction and the right-hand side of this addition or subtraction. And then just like with parsing multiplication or division, we now check to see if there's another addition or subtraction by calling parse addition and subtraction recursively, passing in the remaining string and the binary expression we managed to parse, which has that left, that right, and the operator, which is minus or plus. Now that we've got all of these functions built, we can go ahead and implement parse expression, which is going to first consume any leading white space, then parse the factor, because all of our expressions start with either an integer or a parenthesized expression. And having got that number, that factor, it's going to take that and pass it to and check for a multiplication or division and see if it finds one of those. And having done that, it will take the result of that and pass it to the parse addition and subtraction function to see if there's an addition or subtraction. And that will give you the overall expression. We can wrap this up in a nicer API by creating the parse function, which takes the original source string and returns just an expression. It will call parse expression, constructing this input source class, which represents the state of what we've parsed so far, what was our original input string, and allows us to produce nice error messages. And then if there's any remaining string, if we finish parsing and there's anything left, that must be some sort of error. There must be something on the end of our expression that we didn't expect. So we'll throw an error message saying, look, we were expecting one of these operators. We were expecting addition, subtraction, multiplication, or division, and we got something else. That will allow us to produce, again, that nice error message. If we did manage to parse the whole thing, we can just return the expression. So I promise the parsing bit is the hard bit of this. And in fact, parsing mathematical expressions is especially hard because you have these infix operators. You have these operators that appear in the middle between the two things they operate on for addition, subtraction, and so on. And they also have precedence. So the multiplication and division bind tighter than the addition and subtraction. Most of what you might parse when building a domain-specific language is easier than this. So if you can understand this or just about follow this, you can build one of these languages. So now we get on to what I think is the fun bit, which is the interpreter. And the interpreter is fun because it's much easier, much simpler, fits on a slide. So in this case, we're going to interpret this language. So once we've parsed this, we've got our abstract syntax tree, and we want to evaluate one of these expressions and get a number. It's just a case of having a function that takes an expression and returns the result of evaluating that expression. So in this case, we've only got two types of expression. It's either an integer or a binary expression. And if you want to evaluate an integer, you just return the value. There's nothing else to it. If you want to evaluate a binary expression, you need to first evaluate the left and the right-hand side. That's just recursing into this evaluate function to get the left and right-hand side of the expression. And then once you've got that, you just check which operator you have, and for each operator, we do a different operation. And this is very easy to extend. So if you needed additional abstract syntax tree types, if you introduced identifiers or anything more complex, you just add another case to this switch statement to handle them. So the interpreter is a very easy thing to extend, a very easy thing to add functionality to. The parser is slightly more difficult, but like I say, if you're not dealing with these operators that appear in between the two operands, then things are much simpler usually. So just to check that our example works, because the language we've implemented happens to be a subset of JavaScript, I can do this very easily by taking my example input, taking an example input and checking that we get the same result, whether we evaluate it using JavaScript or we parse it and evaluate it using our domain-specific languages parser. So pros and cons of taking this domain-specific language approach. One of the advantages is it's actually really nice and secure. There's no eval required at any stage. As long as we're happy with those regular expressions, and we kept those very simple, so they should be fine, there shouldn't really be any security issues with this language. It's fast enough for lots of use cases. So there are cases where you might need to actually generate code, compile down to JavaScript. But in lots of cases where you just want some configurability, some extensibility to whatever system you're building, a domain-specific language written in this way will be fast enough to parse and fast enough to evaluate. And if you do have performance issues, you can consider caching the parsing stage. And if you really are struggling, you can consider generating code rather than evaluating, but that will come with a lot of security challenges. A huge advantage to this domain-specific language is it's extensible. You can add your own keywords to this language with completely custom behavior in a way that you can't if you've chosen to implement, say, a subset of JavaScript. It may not be fast enough. That's the biggest downside. Or one big downside, if you do need greater performance, this may require optimization. And the functionality is very limited relative to a general purpose language. So if you start with a general purpose language, there's all sorts of power to structure these things in whatever way you need to. And that can be really beneficial. So if you are building a kind of completely general plugin system, you probably want a general purpose language. In that case, you'll need an alternative. And this is actually, it's a hard problem to solve. I have been working on this myself. So I have an experimental secure JavaScript sandbox, which uses Rust and WebAssembly to properly sandbox JavaScript code. And you can find my work in progress on GitHub, but I am pretty new to Rust and it's a pretty new project. So if you're going to use it in your project, it's, do so at your own risk. But I fully intend to keep working on this. And I have a use case for it myself. So we will be running it in production where I work at some point once we're happy that it's stable. And this will allow us to run arbitrary JavaScript from users in a fully sandboxed way. And I think give us, in some cases, a better extensibility option than having our own domain-specific language. So if you're going to create your own domain-specific language, remember operator precedence is hard, as are infix operators, but the rest of parsing is much easier by comparison. Remember, you can't parse nested parentheses with a regular expression. It's literally not possible. That's what the regular bit means. And you'll be much better off using lots of small functions for your parsing that each have a simple regular expression. That's much more likely to lead to secure and reliable code. Now, I've got a little bit of time left, so I've got two more things to share with you that are only very vaguely related. The first is an open source project I've been working on for a while called @databases. So if you're writing backend code and you need to query databases, this gives you a type-safe API for inserting, updating, and deleting records within databases, as well as queries. And unlike libraries like Prisma, it also gives you a secure, reliable way to write SQL. So I've been saying that there are times when you don't want to create your own domain-specific language, and doing database queries or complex database queries is one of those. SQL is pretty good. It's worth the effort of learning, and you're better off learning SQL than some custom domain-specific language built as part of one individual client. So @databases lets you write SQL directly, and it does so in a way that is secure and safe and cannot lead to SQL injection vulnerabilities. So if you're new to writing SQL, new to interacting with SQL databases from the back end, this gives you a way to do so securely and reliably and without lots of the risks that come with other approaches. Also, @databases supports interactive transactions that can contain multiple different queries and can operate on multiple different database tables at the same time. Again, this is something that not all of the other database libraries provide, and in those you can mix both raw SQL queries and type-safe database interaction. And @databases supports lots of different databases, so Postgres, MySQL, SQLite, even things like BigQuery, and it does support Expo. So if you're wanting to use a database in your React Native applications, you can also use @databases. And if you're interested in this, you can find all the documentation at @databases.org. And one final thing, I work at Mavenoid, and we're currently hiring a senior front-end engineer and senior back-end engineer, and we use React, we use Postgres, we use TypeScript, we use Node.js. So if you're interested in that, please do apply. You can find that on mavenoid.com/en/careers and apply there to either of those roles. And yeah, I'd hopefully look forward to working with you. So if you take one thing away, please don't build UIs that look like this without at least considering the alternative. These are really painful. No shade on the people who did build these. I'm sure they worked very hard on them, and they do work and they are useful, and I've used them, but there are alternatives. Please consider the alternatives. My name is Forbes Lindsay. You can find me on Twitter. Those are the links for @databases and Mavenoid if you're interested in working there. And I will put the example parser up on GitHub at this address. I haven't done so yet, so that is currently an empty repository, but I will upload the example code from this talk to there. Thank you.